Welcome back. In the last video, we completed the introductory section on the Hilbert space chapter, which is chapter 2 in the lecture notes. So just to recap, in that section, we made sense of an inner product. We defined the notion of inner product spaces. We derived a series of basic results, parallelogram identity, Pythagorean theorem, and Bessel's inequality. Then out of those, we pulled Cauchy-Schwarz, and that allowed us to actually prove that an inner product space is a normed linear space if the norm is the, induced norm by the inner product. Then we wrote down one theorem, which is the Jordan-von Neumann theorem, which gives you a very easy but powerful criteria to figure out whether a given norm could be induced by an inner product. This you will prove in the exercises. And then we discussed examples, coordinate spaces, continuous functions with that integral inner product, which is not complete, and then the small L2, which is complete. Now in the next section, we're gonna, I would say, prove one of the very first big theorems that you will encounter in this module, which is the Riesz representation theorem. It might be known from linear algebra, but here this is in infinite dimensional setting. Okay, so to begin with, a few observations here up front. So if you have a Hilbert space, H, if you have any closed subspace, then I claim that is also a Hilbert space. Why is this? Well, you have an inner product by definition in that capital H. So if you restrict the inner product to vectors in the subspace, then this will define an inner product on that subspace. Now, but then what you have to show is that that subspace is, as a inner product space, is complete, and that's why you need the closedness, because this is a result in a metric space module that if you have a complete metric space, then any subspace of it is also complete if and only if it is closed. That's why this statement is true. Okay, keep that in mind. Now moving ahead, we need a new notion. This is convexity. So if you have a subset S of an arbitrary vector space, then it is called convex if and only if, given any two vectors and sort of this parameter theta in 0, 1, this combination here, this is sometimes called the convex combination of the two vectors x and y, is again in the set. So geometrically, that convex combination is, just a straight line. If you think about R2, you have two vectors x and y, 2 points, and then theta x plus 1 minus theta y is just a straight line connecting those 2 points. So geometrically, what are convex sets? So easy examples are, of course, the disks in R2. Those are convex sets, because if you have 2 points, then surely that straight line will be in there. Easy counterexamples are, of course, the stars, right? If you have, or let's say something like this, a hat, then this is not a convex set, because, for instance, this point and this point, you can't connect with a straight line that lies fully inside the set. Okay, so this works, but this doesn't work. Of course, here we will be interested in convex sets in infinite dimensional spaces, and then you should not deceive yourselves by these pictures. Okay, good. Now, the first step towards Riesz representation theorem is almost a variational principle which deals with the so-called best approximation. So the best approximation, it might be known from linear algebra. Maybe I will draw a quick picture here. Again, these pictures, they're always good to build some bridges to previous knowledge if you're on finite dimensional spaces, but in infinite dimensional spaces, they're in general deceiving. Okay, so, but nevertheless, I want to build that bridge. So if you are in finite dimensions, and if you look at a subspace, now in R2, there's a classification that the only non-trivial subspaces are straight lines through the origin. Okay, that's a subspace. It's in particular a convex set, right? Because two vectors on that straight line, if you take a combination of those two, it will again be on the straight line. Okay, and now what one does is, at least in linear algebra, at least in my class, if you have here a vector x, so you represent it by an arrow from the origin, you can project onto the subspace. Okay, what that really does for you is, so let's draw this. like this. So here's a vector, say in red, because this is actually the best approximation. If this is your y, then if you look at the difference, okay, I should maybe stick to blue, otherwise there's too many colors. If you look at this difference, this vector here, this is x minus y. Okay, and this of course is orthogonal, that will play a role later. And if you had changed your vector y, if you had taken a shorter one, for instance, then that difference vector would be a slanted one, like this, okay? And you can see that that slanted one, it is longer. If you look at the length of that vector, it is longer than this one, which I took from the first choice of y. And that's what geometrically is behind the concept of the best approximation. Okay, so let's read the statement. This works in infinite dimensions. So let S be a closed convex set, just like this green subspace there in R2 in a Hilbert space. R2 is a Hilbert space, just like the dot product. And X, the pink one, an arbitrary vector. And the claim is there exists a unique vector Y, that would be the red one, in the closed convex set, which is called the best approximation of X by vectors in Y, such that this holds. So that vector Y, if you look at the difference X minus Y, this is exactly this guy here, its length, it is minimal across all those lengths of the differences, X minus Z for any other Z in S. And that's what I tried to indicate when I drew the second one, because this one here, which comes from the shorter one, say, that would have, would be longer, right? So that here, this guy here is the best approximation. And that's what's written out here, okay? Proving this in infinite dimensions, this is super easy because you can write down formulas. You just use the orthogonal projection of the purple vector onto that straight line. Now here in infinite dimensions, that's harder, right? So, but we will prove it. And as it turns out, this theorem is a beautiful application of the parallelogram identity. Okay, so let's get started. By the parallelogram identity, so let me quickly remind you of that guy. So this was a minus b squared plus a plus b squared is twice a squared plus twice b squared. This is the parallelogram identity. Now here I will apply this for, this is sort of a warm-up computation what I'm doing right now. We will find now an identity that we will exploit several times in the proof. So let's take X, that's that arbitrary vector in the Hilbert space, and some quantities W, right? Then if you stick it into that parallelogram identity and you kind of simplify a little bit, you pull out factors, that's easy to understand why it spits out what I'm about to write down. So 1/4 W2 is equal to 1/2 X minus W squared and then X minus W squared. Right, the right hand side you can spot immediately, and then what I think happens is you divide the whole thing by 4 and then you have this. Okay, so this is, we will use that as a helper in a few moments. Now, let's get started. So what we will first do is we will prove that there is at most one best approximation. And then once this is established, then we will show there's at least one, and then we'll have the theorem. Okay. So let C be the infimum over all those distances. So Z and S. So you just look at X is fixed from the get-go, and now you vary Z over the closed convex set, and then you take the sort of the smallest of those lengths. Okay. If there are W1, W2 in S with, so if there's two minimizers with X minus W1 is equal to X minus W2 is equal to C, then since convexity tells you, remember here in my equality I have this combination, but that's exactly a convex combination of these two vectors for theta equals 1/2. So 1/2 w1 plus w2 is in S by assumption. What do we get? We have on one hand that because C is the minimizer, so C is going to be less than or equal to, well, x minus 1/2. This one, right? Because C is the infimum, so any other vector in S, if you look at the difference to x and take the norm, it should, be at least as big as this minimal distance. And then what you can do is, of course, artificially you can square it. So by the yellow star, what you get immediately is, well, the first quantity, I will derive an inequality here now. So you will have a c squared plus, now the second one, that quarter that you will just leave as is. And then the upper one, because it's an inequality, is 1/2 c squared plus 1/2 c squared. Because x minus w1, that's precisely your c. Right? So you have this. Now this is equal to c squared. So what you have here is, after some simplification, this and this goes out. So you have that a norm is less than or equal to 0. Right? And that, of course, can only happen when the norm is equal to 0. Hence, w1 minus w2 is equal to 0. So by the positive definiteness of the norm, indeed, these two guys have to be equal to each other. Okay? There is at most one minimizer. Okay? Now we will show that there's at least one minimizer, and then combining those two parts together, we will be done. Okay? Next, so C is an infimum, right? So now you can use your definition. You can either subtract a small quantity and then find immediately something in S which would then exceed that thing, or you can use sequences in S. That's what we will do. Next, by definition of C, there exists sequence yn in S, so that, well, we have x minus yn. So this quantity, as n goes to infinity, it will converge to the C. Now here I will do again some algebraic trickery. This is just to have some, nice formulas later on, so you can have, for instance, this estimate, sort of squeeze theorem type estimate. So you have this. Okay, we now show that yn is Cauchy, and then the standard argument sort of applies, because S is closed, right? This was a comment I made earlier. If you have a closed subset of a Hilbert space, then it's itself a Hilbert space. So once we show that yn is Cauchy, then it will have a limit in S, and that guy will be our minimizer. Okay. So it's non-constructive proof. That's the big difference to linear algebra, where you actually write down a formula for the minimizer. Okay, indeed. Why is it Cauchy? Well, yn minus ym squared, and now we're going to use again the same trickery. So you do x minus yn minus x minus ym. So x is the point fixed up front in the Hilbert space. And now you use again parallelogram identity. Parallelogram identity. Maybe up front one would be tempted to use sort of triangle inequality, but that unfortunately doesn't get you to the finish line. So let's use the parallelogram identity. So you can easily check that this is equal to, right, so parallelogram identity here is a minus b, and then there's a relation to a plus b in norm squared. So we have this plus 2x minus yn squared, and then minus 4 times x minus a half yn plus ym squared. Okay, one more time, since yn is a sequence in S and S is convex, that means this guy is in S. So you have a bound for it through the minimizer. For the first two terms, you're going to use this line up here. So x minus yn squared is at most c squared plus 1 over n. So 2 times, here n is m, so c squared plus 1 over m. Then the same thing with m replaced by n. And now, since this is in S, this is at least the third quantity here. This is at least as big as the minimizer. And since there's a squared, it's at least as big as the minimizer squared. And that's good because you have a minus here, right? So that gives you now an upper bound of the form minus 4c squared. All right? And then what happens here is you got a 2c squared and a 2c squared minus 4c squared. It goes out. And at the end, you survive with 1 over n plus 1 over m. And that guy, of course, as nm become large, will go to 0. All right? Hence, since S is complete, because it is a closed, it is a closed set in a Hilbert space. Since S is complete, we have yn goes to a limit as n goes to infinity. Okay, and that limit, that is of course important, because it's closed, it lies in the space, right? You're not falling out. This is in S. Okay, good. Now, using again the yellow star above, we find that x minus y infinity is indeed equal to c. So how do you conclude this? Well, maybe here in green. So the yellow star, that's on the previous slide. So the yellow star was x minus yn squared is squeezed in between c squared plus 1 over n and c squared. So what you do is you start with this guy here. This is at most x minus yn plus yn minus y infinity. Okay, that's right. So now you have control over the second term because you just showed that this guy here goes to 0. Okay, and over the first term you have control by the yellow inequality. Okay, it's squeezed in between, well, c on the left and then square root of c squared plus 1 over n on the right. So as n goes to infinity there, you will converge to c, and that's why this equality up there is true. Okay, this completes the proof. All right, so to summarize, we have the best approximation theorem now. If you have a closed convex set in a Hilbert space, take an arbitrary point x, then you can find best approximation of x by vectors in your closed convex set. Okay, good. It generalizes that picture that I drew earlier, and now in that picture what I did is I drew a 90-degree angle somewhere, right? So now we will have a similar result of this type here in the infinite dimensional world, but for this we first need a short definition, which is the orthogonal complement. So for any subset S in a Hilbert space H with inner product, define its orthogonal complement by, well, that's the stuff which is orthogonal to everything in the given S. So these are all vectors y in the Hilbert space such that they are orthogonal to everything in S. So the inner product of y and x is equal to 0 for everything in S. Okay, and notice, by the way, this definition here works for any subset. You don't need to have a subspace. Okay, in turn, though, that orthogonal complement is always a subspace. This is linear algebra knowledge. And now functional analysis knowledge would reveal that actually the orthogonal complement is a closed subspace of H. Okay, think about that. It has to do with the continuity of the inner product, right? And Cauchy-Schwarz inequality. If you take a sequence of vectors in the orthogonal complement that is convergent, all that you have to do is you have to argue why you can sort of interchange here evaluation of the inner product and the limit operation, right? So once this is okay, then you're done, right? Because the left-hand side would be equal to 0. That right-hand side, this would be your limit, and then you show that the limit is also in the orthogonal complement, hence the orthogonal complement is closed. So you only have to think a little bit about this one. All right, good. Now let's write down the best approximation theorem in the language of orthogonal complements. I showed this earlier in the picture. So let S be a closed, so now let's work with subspaces. Earlier we were just doing convex sets. This was sort of the minimal assumption in a Hilbert space H. Let X be in H and Y in S be the best approximation of X by vectors in S, then the difference vector X minus Y is, well, in the orthogonal complement of S. Okay, and this is what I had earlier in my picture. So here in R2, take a subspace which is straight line through the origin. You take your vector here, X, then the orthogonal the best approximation is the orthogonal projection. We don't know that language yet here in functional analysis, so maybe let's not use it. And then the X minus Y vector is this one, and this one is obviously orthogonal to the green line. And right, that the orthogonal complement of the green line has to be a subspace, so it is precisely this one, right? This is your S and this is your orthogonal complement. And that's precisely where X minus Y lies on. Okay, that's the geometry. Now here, of course, infinite dimensional cases, I can't draw pictures. Yeah, I should have used different color. Proposition. And now proof. And then we will be done for this video once we have proven it. So since X minus Y is this minimizer, so infimum over all these differences where Z is in S, we have for any lambda in C and Z in S that X minus Y is at most X minus Y minus lambda Z, right? Because Y, the best approximation, is a vector in S. Since S is a subspace, this guy here is in S, right? And since that is the minimizer, well, that means it cannot exceed this difference for another vector in the subspace. Okay, so now you use equivalently, so you maybe want to square both sides. X minus Y squared less than or equal to X minus Y minus lambda Z squared. Now this time we're not going to use the parallelogram identity anymore. We're just going to use that X minus Y squared is, well, it is sort of part of the parallelogram identity. It's used in the proof. We use this guy. Okay. So here this will be X minus Y squared, then plus, then this guy squared. Well, this is by the norm properties lambda complex modulus squared and then length of Z squared. and then there will be a minus twice the real part of x minus y lambda z. Okay, as you can see, this guy and this one, they go out, and this is an inequality, so what you have just established it. So you have that minus twice the real part of x minus y lambda z plus lambda squared z squared is non-negative. You can write it this way, or bring that inner product on the other side. Hence, with lambda in polar form, lambda ei theta, theta in 0 to pi, so you insert it here, then you can cancel out something. After the cancellation, you take the limit as lambda goes to 0 in complex modulus. What you find is minus twice the real part x minus y ei z is non-negative, and this works for all theta in 0 to 2 pi and any z in S. Okay, z was an arbitrary point. Okay, now almost done. Now I claim this allows you to conclude that the real part of x minus y z has to be equal to 0. And why is this? Well, look, you can now freely choose your angle here. So if you choose the angle theta equal to 0, then you would have minus 2 times that real part is non-negative. So it would tell you that the real part is non-positive. Yeah, but then if you choose, in the next case, theta equal to pi, then you get a minus sign here. So you would have now that the real part x minus y, inner product x minus y z is non-negative, right? So these two inequalities put together gives you that, well, this guy has to be equal to 0. Yeah, but now what you need is, you also need that the imaginary part is 0. And how do you do this? Well, you take theta equals to pi over 2, and this becomes an imaginary unit. This here becomes imaginary unit. You pull it out with a minus sign, and then you have real part of I times inner product, and that precisely gives you an imaginary part. You do this, and then finally you do it for theta equals 3 pi over 2, and that allows you to conclude overall that also the imaginary part is equal to 0. And well, this means altogether that x minus y z is equal to 0 for all z in S. So, by definition of the orthogonal complement x minus y, that difference is in the orthogonal complement. And that's the punchline. Okay, good. That's all that I want to do in the video. The next video, in the next 2 videos, we will prove then the Riesz representation theorem. Okay, I will see you then.